Hello everyone. In this lecture, we will see the relation between the speed, slip, and how the slip varies along with the slip. As we have seen in the previous lecture, the types of the rotors, also what is the concept of the rotating magnetic field, and in the brief at the end, we have also seen the relation between the slip and the rotor speed. So let's start with the again briefly discussing the principle as we have stated in the previous lecture also, that induction motor creates a rotating magnetic field, which is also known as the RMF, through the stator winding, and that rotating magnetic field rotates on the synchronous speed, which is known as the ns, and it equals to the 120 f over t. So taking this into account, uh, f is nothing but the supply frequency, P is the number of poles, and Ns is the synchronous speed in RPM, and Nr is the, we will take that as a rotor speed. So there are three scenarios which we have taken over here. If let's suppose your synchronous speed becomes equals to the rotor speed, or the rotor is rotating at the synchronous speed. So what it happens, the d phi by dt, which is happening due to the relative speed between the rotor and the stator magnetic field, that will becomes zero because both are rotating on the same speed, and there will be no relative speed between that, and there will be no the d phi by dt will happen. So therefore, in that case, what happens, my rotor will stop because there will be no induction phenomena will happen, and there will be no induced EMF, and therefore there will be no current in the rotor bars. So it will stop my rotor. Second is, let's say that the synchronous speed is more than the rotor speed, or my rotor is rotating less than the synchronous speed, which is very obviously the actual scenario happens in the induction motor. So in that case, what happens, the rotor always wants to catch up the rotating magnetic field, and it will always keep on rotating because there is some relative speed between the stator magnetic field and the rotor. So therefore we will have the d phi by dt, they will have the induced EMF, which further flows the current in the rotor bars, and then due to the induction phenomena, my rotor starts rotating or keep on rotating. The third scenario, which is very interesting, that my rotor is rotating on more than the synchronous speed. So this is a case of the induction generator, and it is something like that, which happens on the also in the EVs, and it is known as the regeneration, or the regenerative braking happens due to this. So what happened in this case, let's say my vehicle is going on the downhill, it is going on the downhill. So in that case, what happens, so what happened in this case, if I'm going downhill, very obviously my rotor, which is rotating due to the shaft movement, and if somehow, if I can manage that synchronous speed gets lower than my rotor speed, because rotor speed is totally depending on the decline hill. So as you are going decline hill, my rotor is keep on rotating without any external supply. So in that case, what happens, if I can reduce the frequency of the supply by some mean, so therefore it will directly reduce my synchronous speed. And if that synchronous speed less than the rotor speed, the induction motor now will behave as an induction generator. So in that case, the regenerative braking happens, and in case of the EV, that produced power, or that produced generation fetch back to the battery supply to charge the batteries. Something like that, that my rotor is is rotating behind the rotating magnetic field, so it will always try to catch up the rotating magnetic field, whereas the rotating magnetic field, which is shown over here, is rotating on the synchronous speed. So this is the case of the motor principle. If this rotor is rotating more than the speed of the RMF, then it will become an induction generator, and rotor will always try to catch up the rotating magnetic field, but it will never try to able to achieve it in case of the motor action. And something like that, that a hose is always try to catch the carrot. So here the caret represents my rotating magnetic field and a hose represents a rotor. So now we have come to the relation to the slip and speed. As we know that the ns is the synchronous speed of the rotating magnetic field, nr is the speed of the rotor. So slip is given by ns minus nr into ns, and in percentage, if I'll multiply it with the 100, then it becomes into the percentage. Now let's take this scenario. Assume it that my slip is 0. So therefore, again, it says that that ns becomes equals to nr. In that case, only my slip will become equals to 0. But as I've stated that it is it is not going to happen anytime. So ns will not become equals to nr at any time. Induction motor when behave as an induction generator, something like which I've stated, like if my EV is going downhill, then only the rotor is rotating by itself, and in that case I have to reduce my synchronous speed by varying the slip, because if my synchronous speed given by 120 f over p, so number of poles are something like which is fixed once I have made my motor, but the supply frequency is in my hand and I can easily vary the supply frequency. The second scenario is let's say slip is 1. So this scenario is known as the standstill. I mean, if the slip is 1, and as I've taken already this formula over here, let me written again it, that slip is ns minus nr upon ns. So if my slip is 1, so that's sufficient that nr is going to be the 0. So that's what's represent, but motor is not rotating, it is at standstill. So slip 1 is equals to that rotor is at standstill position. And the speed of the rotor, if I want to find out the speed of the rotor if the slip is given, so just let's take this uh, formula again, that s is equals to ns minus nr upon ns, and taking that into account, my nr becomes equals to s into ns, and this becomes minus of ns and minus of it. So I will have a relation which is ns into 1 minus s. And frequency of the rotor, because the supply frequency which I'm giving it is going to the stator winding, and my rotating magnetic field is also rotating on the same frequency which is I'm giving to the supply, but the rotor frequency is given with fr is equals to n slip into p divided by p, or I can say that p into ns minus nr into divided by 120. So this is my rotor frequency, and the relation between supply frequency and rotor frequency is fr is equals to fs divided by s, or I can also say that the rotor frequency is the nothing but the slip time of my supply frequency. So directly I can find out that my rotor, what is the frequency of my rotor. So here I have taken a very simple example over here. Let's say I have an induction motor having 8 pole over here, stated here. Frequency is given 50 hertz, and rotor frequency is 1.5 hertz. At what speed is motor running and what is the slip? So as the supply frequency is given, rotor frequency is given, I know that synchronous speed is 120 f over p. So I will find out the synchronous speed. So synchronous speed of this motor is 750 rpm, and now I have the relation that slip is equals to fr divided by fs. So I can also find out the slip from here. So fr is given 1.5 hertz, fs is given the 50 hertz, so my slip becomes 3.03, and therefore I can find out this now the speed of my rotor. So nr is nothing but 1 minus s into ns. So 1 minus slip into the synchronous speed 750 rpm, so my rotor speed becomes equals to the 727.5 rpm. So it is directly indicating that my rotor is always lagging behind the synchronous speed, and the slip is which defines that how much my rotor will lag by the my rotating magnetic field. Again, quickly taking the types of the rotor here. As I've stated that we have the two types of the rotor in induction motor. One is the slip ring rotor, also known as the wind rotor, and the other one is the my squirrel cage rotor. So here, in case of the slip ring induction motor, we have the rotor bars, and in between the rotor slots we have the windings placed over here, three-phase winding. All these three-phase windings are connected through the slip rings. So as my rotor rotates, my slip ring also is rotating along with it because it is implemented on the shaft. And here I have again given a brush arrangement just like in case of the DC motor we have seen it. So for the three-phase rotor, we have the three brushes over here, carbon brushes, each on one slip ring. So this is for one phase, this is for another phase, and third one is with the another phase. So by this means we give the supply to my rotor three-phase winding. As the rotor is keep on rotating, so I have to apply some arrangement by which I can give the supply to my rotor windings. What are the advantages of it? This is the equivalent circuit of my slip ring induction motor. So here it shows a three-phase winding over here. So all these three-phase winding are connected over the, let's say, through it is connected over the slip ring, and slip ring have the brushes over it. So these are the brushes, and if I'm giving supply to it through the brushes arrangement, I can also insert a resistance over here. What it does, it creates, I can insert the external resistance, and when we will see the torque relation for the induction motor, there we will see that how the rotor, the resistance of the rotor, if I increase it, then how it also increases the starting torque, and how it can also control my starting current. So that is the advantage in the case of the slip ring rotor, but it is less efficient because of the brushes over here, costly because of this arrangement, the brushes and the slip ring, and this is a complex construction, so it has a complicated construction. So where we need to achieve the high starting torque, so there we have to implement the slip ring induction motor. However, in case of the squirrel cage rotor here, we can easily see that these windings are nothing, it's not the rotor windings, these are windings are the which is shown as the stator windings. Stator is invisible over here, just winding are shown. And just to show that how my poles are created over the stator winding, just one pole set is shown over here, and the rotor of the squirrel cage having the rotor bars, which is short circuited by the end rings of the aluminum over here. So it does not have any winding arrangements over the rotor, so we don't require any slip ring or any brushes arrangement over here. So it is very simple. However, in this rotor case, we don't have any option to increase the rotor resistance, so we cannot manipulate the torque at the starting. So therefore we don't have any control through the rotor in case of the squirrel cage motor to manipulate the starting torque. However, it has a very simple construction as there is no brushes in slip ring, so it is more efficient than my slip ring induction motor. But the limitations are that it will give you the low starting torque as compared to the slip ring induction motor, and high starting current, because we don't have any options to improve or increase the rotor resistance. So we don't have any control over the starting current also through the rotor arrangements. We do have the other arrangements by which we can control the starting current, but by improving or by increasing the rotor resistance, we don't have that option in the case of squirrel cage induction. So I hope it is clear. In the next lecture, we will see the torque slip characteristics and also a relation the torque for an induction motor, and we will see that what are the variables which affects my torque of an induction motor. Thank you very much.